Hello friends, welcome back to Survival Roots. If you are a homeowner trying to build smarter, a DIYer who cares about durable materials, or someone simply tired of paying too much for basic comfort, this one is going to hit close to home. You know that feeling when winter settles in, the air outside bites your face, and you open the latest heating bill only to wonder how the cost got so high while the house still felt cold by sunrise. The furnace kept running, the meter kept spinning, and somehow comfort still never matched the price. Now here is where things get interesting. In the bitter cold of Newfoundland, a man named Eddie Roberts put together a simple solar heater for less than $50. No expensive equipment, no complicated electronics, no flashy modern system. He used aluminum cans, black paint, a basic framed box, and a glazed front panel to capture heat from the sun and move it where it was needed most. And the result was not just impressive, it was hard to ignore. Air entered the collector at around 60 degrees Fahrenheit and came back into the room at more than 218 degrees. That kind of performance gets your attention fast, especially when it comes from low-cost materials and straightforward building logic. Today, we are taking a serious look at the device many people call the Alaskan System. We are going to break down why it works, why simple ideas like this rarely get promoted by the mainstream heating world, and what it can teach us about building better with practical, affordable materials. By the end of this video, you will understand the core idea, the real value behind it, and why forgotten building knowledge still matters today. So before we get into it, make sure you subscribe to Survival Roots, because around here, we do not chase hype. We dig into real-world solutions that help you build warmer, smarter, and more independently. Part 1. The physics of garbage. How it actually works. So now the real question is this. How do you get air temperatures above 200 degrees from what looks like a stack of scrap aluminum and a simple box on the wall? The answer is not magic, and it is not marketing. It is one of the oldest and most dependable principles in building science: thermosiphoning. To see why this matters, look at a real example from the Lake Michigan snow belt. A builder named Guy Sperry put together his own collector using 240 aluminum cans, a polycarbonate glazed front, and an aluminum frame. On a day when the outdoor temperature was just 4 degrees Fahrenheit and the wind was cutting hard across the lake, the temperature inside his collector reached 172 degrees. Even more impressive, his furnace never kicked on, and his 970-square-foot home stayed warm using nothing but sunlight and a carefully built panel made from recycled materials. Here is what is happening inside that box. Sunlight passes through the clear glazing and strikes the black-painted cans. That black surface absorbs solar radiation efficiently, and the aluminum moves that heat fast. This is one of the reasons aluminum works so well in practical low-cost builds. Its thermal conductivity is about 205 watts per meter Kelvin, far higher than steel, so the heat does not linger on one spot. It spreads quickly through the metal and into the air moving through the system. And this is exactly why the cans matter. A flat metal sheet can get hot, yes, but stacked beverage cans create something even more useful. The concave bottoms of modern cans form internal disruptions as the air moves upward through the column. In simple terms, they stir the airflow. Instead of sliding through in a smooth layer, the air tumbles and mixes, which increases contact with the heated surface. In heat transfer, that is a major advantage, because moving air absorbs more energy when the boundary layer is constantly broken up. Then the second part of the system takes over. As air warms, it becomes less dense. Warm air naturally rises, and once it starts moving up and out through the upper vent, it pulls cooler, denser air in through the lower vent. That creates a steady, self-feeding convection loop. No complicated controls, no constant power draw, no expensive machinery. The sun provides the input, the material choice improves the transfer, and the airflow does the rest. That is the real genius here. It is not just cheap, it is smart, passive, and based on physics that have been proven for centuries. Part 2. A history of the forgotten sun. And once you understand that principle, something else becomes clear. This is not some trendy internet trick that appeared out of nowhere. What you are looking at is old knowledge, rediscovered again and again by people who understood how to work with climate, material, and orientation instead of fighting all three at once. Go back to 1767. High above Geneva, Swiss scientist Horace Benedict de Saussure built a simple wooden box with a glass top and a black interior. He called it a hot box. Under direct sunlight, that box reached around 230 degrees Fahrenheit. What makes that experiment so important is not just the temperature, it is the fact that he carried the idea into the freezing Alps and found that the system still worked. The glass let solar radiation in, the dark interior absorbed it, and the enclosure held the heat. That is the same design logic we still use today. But even that was not the beginning. More than 2,000 years earlier, in the Greek city of Olynthus, planners laid out streets so homes could face south and collect winter sunlight. This was not treated as a luxury feature or an optional upgrade, it was simply good design. Buildings were oriented to serve the season, and passive solar gain was part of how a settlement functioned. Even in that era, people understood that ignoring the path of the sun was poor planning. Then look at Mesa Verde, where the Anasazi built dwellings into the sandstone cliffs. Those overhangs blocked the high summer sun, but welcomed the lower winter sun deep into the structures. Thick stone walls stored heat during the day and released it slowly after dark. No furnace, no ductwork, no fuel deliveries, just geometry, thermal mass, and careful observation of the environment. So when people act as though solar heating is a new idea, that is simply not true. The deeper truth is that we have known how to capture and keep heat for a very long time. What changes across history is not the physics. What changes is whether a culture chooses to build around common sense, local materials, and free energy from the sun, or whether it forgets what earlier builders already knew. And that brings us to the bigger mystery. If this knowledge has been with us for over 2,500 years, why did the modern world walk away from it?
The next question is no longer whether the physics works, but why a culture...
Part 3. The White House Solar Mystery. And that question leads us straight into the next layer of this story. Because the reason this knowledge faded was not that the technology failed, it was that economics, politics, and energy priorities moved in a different direction. In June of 1979, during a period when the oil crisis was shaking the American economy, President Jimmy Carter made a decision that was both practical and symbolic. He installed 32 solar water heating panels on the roof of the West Wing of the White House. These panels were not there as decoration, and they were not some public relations prop. They were doing real work, supplying nearly 75% of the thermal energy needed to heat 1,000 gallons of water for the White House staff kitchen. At the dedication, Carter framed the moment in a way that still stands out today. He said that a generation later, that solar heater could either become a museum piece, a curiosity, a reminder of a road not taken, Or it could become part of one of the most important national efforts the country had ever pursued. That was not just a statement about equipment on a roof. It was a statement about which path the country would choose. And we know how that story turned. A new administration came in, priorities shifted back toward fossil fuels, and the national conversation around energy independence changed with it. In 1986, during roof resurfacing work, Ronald Reagan had those same solar panels removed from the White House, and they were never put back. They ended up stored away in a warehouse in Virginia, effectively discarded and forgotten. But the technology itself was never the problem. In 1991, Peter Marbach from Unity College in Maine tracked those panels down, bought them from the government for just $500, and brought them north on a college soccer bus. Back in Maine, they went right back to doing what they had always done, producing useful heat. In fact, they continued serving the college cafeteria for roughly another 20 years. That is the part people should not miss. The system did not break down. The science did not stop working. The materials did not suddenly become invalid. The technology was pushed aside because cheap oil, centralized energy, and established industry had momentum on their side. So when we ask why practical solar heating was forgotten, the answer is not poor performance. The answer is that we chose another path, even when the old one was still working. Part 4. The regulatory wall. Why is it illegal? And that brings us to the question people ask as soon as they see a system like this. If it works, then why do so few people build it? And why does it feel almost forbidden in the modern housing world? The honest answer is that the Alaskan System was not outlawed through some dramatic secret ban. There is no midnight law aimed specifically at a wooden box filled with aluminum cans. The real barrier is less theatrical and, in many ways, more effective. It is structural. It is regulatory. It is the kind of wall that does not need to say "forbidden" out loud, because the process itself already shuts most people out. If you open the International Residential Code and look at Chapter 14, you find language requiring heating equipment to be listed by a nationally recognized testing laboratory, such as UL. On paper, that sounds reasonable. In practice, it creates a major divide between factory-made products and site-built solutions. A garage-built solar air heater that may cost you only $50 in materials can require certification costs ranging from $15,000 to well over $100,000 before it is recognized as compliant in a formal inspection setting. Now stop and think about what that means from a building perspective. A homeowner can understand the materials, build the frame, manage the airflow, and create a system that clearly produces heat. But without recognized certification, an inspector may reject it, a permit may not be issued, and an insurance company may refuse coverage if something goes wrong. That is why so many owner-builders hit the same wall. The issue is not always whether the system works. The issue is whether the system fits inside a framework built around commercial manufacturing and formal product listings. And then there is another layer: homeowner associations. In some cases, even when a solar installation is functional and technically sound, it can still be challenged because it does not fit neighborhood rules or aesthetic guidelines. The story of Thomas Farwig in North Carolina became a powerful example of that tension. He installed solar panels, and his HOA responded with massive fines tied to architectural restrictions. In many states, there are still weak protections, or no meaningful protections at all against that kind of opposition. When you step back, the bigger picture becomes easier to see. The traditional HVAC market is worth more than $156 billion a year. That industry is built around equipment sales, service calls, fuel use, electricity demand, and long-term maintenance. A simple solar air heater made from low-cost materials asks for none of that. No monthly fuel bill, no service contract, no subscription model, no complicated machinery to maintain. So is it truly illegal? Not in the dramatic way the headline suggests, but it exists outside the kind of system that modern codes, permits, insurance structures, and neighborhood rules are designed to favor. And for the average homeowner, that can create almost the same result. It is not banned because it fails. It is pushed to the edges because it does not generate the kind of controlled, metered, product-based value that the larger system is built around. Part 5. Building your own $50 Freedom Box. So once you understand the science and the barriers around it, the next question is the practical one. How do you actually build one yourself? And this is where the idea becomes even more appealing. Because despite all the attention-grabbing numbers, the basic construction is surprisingly straightforward. With a weekend of careful work and a smart choice of materials, you can put together a collector that is simple, affordable, and genuinely useful. It starts with the box itself. You want a shallow wooden frame, strong enough to stay square and sealed, but not so deep that you lose efficiency. Material choice matters here. If possible, avoid pine, because under repeated heat it can bleed sap and create a mess inside the collector. More important than the frame, though, is the insulation. A good collector is not just about capturing heat. It is about keeping that heat from escaping in the wrong direction. That means the back and sides need rigid board insulation to reduce thermal bridging. Skip that step, and the panel can work against you after sunset by letting valuable indoor heat leak right back out. Next comes the heart of the system, the cans. Depending on the size of your panel, most builds use anywhere from 72 to 200 aluminum cans. They need to be cleaned well, then modified at the bottom to create the internal turbulence that improves heat transfer. After that, the outer surface should be scuffed with sandpaper, so the paint has something to grip. This may seem like a small detail, but good surface prep is one of those things that separates a quick build from a durable one. Once the cans are ready, they are joined end to end into long vertical tubes. High-temperature silicone is commonly used here, and some builders also rely on metal tape in specific areas to reinforce the seal. The goal is simple. Keep the columns straight, stable, and as airtight as possible, so the airflow stays controlled from intake to exhaust. Then comes one of the most important finishing steps, coating the absorber surface. The full can array needs a flat black finish because black surfaces absorb solar energy far better than reflective ones. Most builders choose high-heat barbecue paint or engine enamel, since a collector can reach very high internal temperatures when it sits in strong sun with limited airflow. The right coating helps the system absorb heat efficiently, without degrading too quickly over time. Finally, the front gets sealed with glazing, usually tempered glass or polycarbonate, depending on budget, weight, and durability goals. Then you create the airflow path itself, a lower intake opening and an upper exhaust opening. That setup alone can run passively through convection, but many builders take it one step further by adding a small 12-volt fan powered by a compact solar panel. That upgrade turns a passive heater into an active one, and the beauty of it is the built-in logic. When the sun gets stronger, the fan runs harder, and the system moves more hot air exactly when more heat is available. It is a simple build, but when the materials and details are handled correctly, it becomes a very clever piece of low-cost building science. Part 6. The invisible danger. Safety first. But before anyone gets carried away and starts cutting holes in a wall, there is one part of this project that deserves serious attention, because it is the part too many online tutorials rush past. And in real-world building, the details people skip are often the ones that matter most. The hidden issue here is off-gassing. When you spray paint aluminum cans, especially with conventional aerosol products, you are introducing volatile organic compounds, or VOCs, into the system. Many common spray paints contain chemicals such as toluene, xylene, and acetone. These are not harmless leftovers. In the wrong concentration, they can irritate the lungs, affect coordination, trigger nausea, and create a very unhealthy indoor environment. Now here is where the danger increases. Inside a solar collector, those painted cans can easily reach temperatures of 140 or 150 degrees Fahrenheit, and in some situations, even more. At those temperatures, chemical off-gassing can accelerate dramatically. So, if a freshly painted collector is connected directly to the house too soon, what you are doing is not just moving heat indoors. You may also be sending concentrated chemical fumes straight into your living space. That is exactly the kind of mistake that turns a good idea into a bad outcome. So the safety protocol here is not optional. Before the collector is ever connected to the home, it needs to go through a full bake-out period outdoors. Set the completed unit in direct sun. Keep it vented openly to the outside air, and let it heat cycle for several days. This gives the remaining solvents time to evaporate and clear out before any of that air is introduced into the house. The rule is simple. If you can still smell it, it is not ready. And there is one more layer to that same common-sense approach. Hot air discharge points need proper clearance from combustible materials. Curtains, bedding, paper, and other flammable items should never be allowed near the outlet. A system like this may be simple, but it still deals with concentrated heat. And every good builder knows that affordability never excuses poor safety planning. That is the real lesson here. True self-reliance is not about throwing something together and hoping for the best. It is about understanding the materials, respecting the risks, and building in a way that is not only effective, but responsible. Part 7. Real-world triumphs and the hybrid future. So after all of that, the question becomes very simple. Does this kind of system actually change anything in real life? Or is it just a clever experiment that looks good on paper? And this is where the story gets even more interesting, because there are real cases that show this is not just a backyard curiosity. In the cold climate of Newfoundland, Jim Meany got tired of watching high diesel and electric heating costs eat away at the family budget. So he began experimenting with solar air heating and eventually developed a commercial version known as Can Solaire. What matters most is what happened for the people using it. One homeowner in Nova Scotia had been going through 4 full tanks of heating oil every winter. After installing 2 solar air units, that number dropped to just 1 tank. Think about that for a moment. That is not a tiny adjustment or a barely measurable gain. That is a major reduction in fuel use, and it tells you exactly where systems like this have real value. They may not replace everything, but they can dramatically reduce how hard your main heating system has to work. And there is another example that pushes this idea even further. In 2019, a group of mechanical engineering students at the University of Washington, Bothell, built a soda can solar heater for a tiny home project designed to support housing for the homeless. Their panel measured just 3 by 6 feet, yet it produced 2,246 BTUs of heat. For a 125 square foot structure, That represented nearly half of the home's total heating demand. That is an impressive result for a collector built from inexpensive materials and straightforward engineering. But what really stands out is what they did next. Instead of treating the solar heater as a standalone novelty, they integrated it with an air source heat pump. Anyone familiar with cold weather performance knows that heat pumps become less efficient as outside temperatures fall. The students improved that situation by routing the preheated air from the solar collector into the heat pump intake. So instead of forcing the heat pump to work with 30-degree outside air, they fed it air closer to 105 degrees. That one change greatly improved the system's coefficient of performance, allowing the heat pump to deliver more heat for the same electrical input. And to me, that is where the future really starts to come into focus. It is not about rejecting modern equipment or pretending every old idea should replace every new one. It is about combining time-tested passive solar principles with efficient modern systems in a way that makes both perform better. When a collector like this can contribute 5,000 to 8,000 BTUs of free heat during sunny hours, your furnace or heat pump cycles less often. Your fuel or electrical use drops, and your heating bill can fall by 20 to 50%. That is not fantasy. That is what happens when smart building logic and practical technology are allowed to work together instead of competing with each other. The power in your hands. So now, let's come full circle and think again about that winter utility bill. The one that shows up in the mailbox while the cold air cuts across your porch and the furnace keeps humming in the background. For millions of households, that bill is not just frustrating, it is exhausting. More and more families are falling behind on energy payments, and the pressure of basic heating costs keeps growing year after year. Now, let's be honest about what this system can and cannot do. The Alaskan System is not going to keep a huge 3,000 square foot house at 75 degrees through the middle of a midnight blizzard all by itself. It is not a magic box, and it is not a complete replacement for every conventional heating system. But that is not really the point. The deeper power of this design is what it represents. It proves that with a small amount of money, recycled materials, a sheet of glazing, and physics people have understood for centuries, you can take part of that heating burden back into your own hands. That matters, because the moment you build something like this, you begin stepping outside a system that expects every bit of comfort to come with a recurring bill attached to it. You learn the materials, you understand the airflow, you test the design, you improve it. And once you do, that knowledge becomes something you can share. You can document it, teach it, and pass it to someone else who is just as tired of paying more and getting less. So, imagine for a second, what would happen if millions of homeowners decided to capture even a small portion of their heat for free? Imagine how much money that would keep in ordinary households, and how much resilience that would add to communities that have become too dependent on centralized systems for basic survival. If this video gave you a new way to think about heat, building, and self-reliance, hit the like button, share it with someone who is sick of outrageous heating bills, and subscribe to Survival Roots so you do not miss what is coming next. In our next deep dive, we are looking at a wood heater that burns at 1,300 degrees inside while sending only 100 degrees out the chimney. Until next time, stay warm, stay curious, and keep growing those survival roots.